Well, good morning, everybody. It is 7:40, so we're going to get started here. Good morning, Dahlia. Good to see you and everybody else who's with us in here. It is Monday, November 2, 2020. And today looks like we've got... It's to be very still right now. I see no wind. Appears that the weather is, you've got some misty clouds very high up in the atmosphere. But it would seem as though these clouds will likely burn away as the day goes on and give way to nothing but blue skies and golden sunshine all the day long. So, happy Monday to you, and let us begin talking where we left off last class about the scientific revolution, and we talked to a good deal about just how radical the scientific revolution was, in the sense that it really changed the way that people began to think about how the world works. It also created a very long shift away from associating knowledge with the past and instead beginning to build an understanding between knowledge as being a product of future discovery. So, whereas in the beginning of the scientific revolution, the general societal view of Europe would have been that if you wanted to learn something, everything was at one point already known, if not discovered by ancient civilizations like the Greco-Roman civilizations, then answered by Christianity in the 1500 years that followed. And increasingly, as we move throughout the scientific revolution, we realize that people begin to understand that there's a lot that they don't know, number one, and that number two, revealing knowledge to things that people did not know meant asking new questions and finding new solutions, which means that intrinsically this dig for knowledge, this discovery, this urge to uncover knowledge quickly began to reorient away from people uncovering past teachings and rather focusing on new learnings based on new methods, as well as using new technological innovations, which in particular with respect to astronomy helps us out significantly in beginning to answer some of the mysteries of the universe. So we talked about Nicholas Copernicus towards the end of last class. Nicholas Copernicus came up with the notion of the heliocentric view, and I left off where I went a little bit long last class talking about this diagram that's in the piece that Copernicus wrote. Now, in this diagram, you can see the sun in the middle there, Mercury, Venus, Earth, which is designated by Terra, and then the moon revolving around the Earth. Then you have Mars, Jupiter, Saturn, which to them were the only known planets at the time. And then this Stellarum Fixarum, which sounds like a Harry Potter spell because that's all based on Latin. And basically, this is talking about this immovable celestial outer sphere that kind of is situated around the sun somewhere. Almost like a backdrop to a movie scene or something like that. That just kind of stayed there. And the only reason they appeared to move at all was because Earth was moving. Now, the other thing that's inaccurate about this, aside from the fact that, number one, the sun is not in the center of the universe, okay? It's not even in the center of our own galaxy, of which there are hundreds of billions of galaxies in the universe, all right? But it's not even at the center of our own galaxy. In fact, we're kind of in like, if the sun could be positioned, if we were talking about, positions on Earth, the sun is in like a distant suburb, like an upper middle class suburb somewhere, in a kind of nice, well manicured area of the galaxy. It's not directly towards the center of the galaxy, where the gravitational pull from the black hole in the middle of the galaxy would begin to become disruptive to life on Earth. So the sun is kind of situated in a nice little comfortable quiet spot on one arm of the Milky Way galaxy. And of course, they didn't have any ability to see that far out at this time. I mean, all of the new inventions of telescopes and things that we've made in the last 100 or 200 years are really what has enabled us to uncover much, much more knowledge about the universe and how it operates and so on. So certainly he didn't have this in his time. But what we can say about Copernicus's piece here is that it nonetheless is more accurate than what most people believed at this time, which was that the Earth was this immobile, fixed object in the center of the universe, and everything else in the universe revolved around the Earth, which is, of course, incorrect. What was the religious reaction to Copernicus? Well, immediately, Martin Luther and John Calvin condemned Copernicus's view. Why would they condemn it? Because remember, even though they're challenging the Catholic Church, the Protestant Reformation is challenging the Church to become more strict, more literal in its interpretation of the Bible, okay? The Catholic Church initially actually didn't react as severely to the Protestant Reformation and Copernicus because the Catholic Church had kind of gained a reputation for not interpreting the Bible literally. Because as time had gone on, the Bible became more and more difficult to literally interpret as times changed. And so by the time that we get to the 1500s, we're living 1500 years after Jesus, and there had been some societal developments in that time, and seemingly some of these ancient teachings from the Bible probably needed to be modified to fit in some of the things that were going on at that time. But it does not take long for the Catholic Church to realize that the scientific revolution is a threat to the power it has over people's intellect and over people's beliefs about the universe and so on and so forth. So by 1616, within about a century of Copernicus's book, a little bit less than that, maybe about a half a century, the Catholic Church proclaimed the Copernican view false and began persecuting those who advanced his views, such as Galileo. So this kind of gives you an idea about the religious reaction to it, but because Martin Luther and John Calvin were trying to reform Christianity and the Protestant faiths to be more strict in terms of its interpretation of the Bible, some of these new scientific ideas that are coming out at this time seem to directly contradict what is written in the Bible. And then they're forced to pick a side, and being that the religiosity of people at this time was so strict, it opened the door for people having to pick between which view they supported, and the Roman Catholic Church had a whole lot of believers behind it, and the scientific revolution did not. And so a lot of times erring on the side of caution, but also social pressure, would side with the church in situations where they were forced to make a decision about what they thought about the universe. By the way, this reminds me, I want to make mention of something that I truly messed up, and did not realize I messed up until I came here this morning and checked my email. And I realized that I did not put a prompt up for the extra credit assignment. So what I'm going to do is I'm actually going to extend the extra credit assignment a week. And I'm going to, in fact, maybe I'll just do that right now so I don't forget to do it later. I'm going to go to the extra credit assignment here. And I did not put a prompt up for this because I was so focused on giving you guys all of these instructions down here that I forgot to put the prompt up like a dummy. So I'm going to go ahead and put this prompt right at the top here. Okay. What were the three major causes of the witch hunting era in the age of absolutism? Okay, that is the prompt that I meant to have you guys answer when you did your right. So, Michelle, to be honest with you, there's no real way to do it unless you have the prompt. And so, was that prompt listed in the introduction of the documentary? I don't know. I don't think so. But so anyhow, but this is, yeah, this was the prompt that I meant to have you answer to, but I, for whatever reason, just did not type the prompt out. And so, yeah, each of your body paragraphs will essentially cause another, or address another major cause. Now, here's what you don't want to do. For your three major causes, you don't want to be like political causes, economic causes. Wait, under the thesis statement. I don't think I did put it there. I gave you an example of a thesis statement, but oh, in this essay, everyone's argument will pertain to the main causes of the witch hunts in England. I guess I did. Okay. All right. I guess I did. I just didn't formally write it like this, though. You'll see it written like this on your actual DBQ. I guess I did put it in here. In this essay, everyone's argument will pertain to the main causes of the witch hunts in England. Okay, I guess I did put it in there. All right. My mistake. Sorry, guys. I looked through and I didn't see that, and I was like, oh, no. Okay, all right. Well, if you did it already, then you're good. But I'm still going to extend it anyway, just because... why not? I'll give some folks a couple extra days to do it. I won't extend it for a full week, but I'll extend it another few days just in case that was unclear to you. We gotta go here, edit. I'll make it due Wednesday. How about that? Go over here, Wednesday, and Wednesday. Okay. There we go. All right. Okay. So, okay. All right, now that we've got that taken care of, very good. So, moving on. Whoops. Tycho Brahe, or sometimes it's Tycho or Tycho Brahe. I'm not exactly sure. I'm not exactly 100% sure how to say his name. I think it's Tycho Brahe, but maybe it is Tycho. Anyway, Tycho Brahe, 1546 to 1601. He was Europe's best astronomer in the late 16th century. Now, ironically, Tycho Brahe was a geocentrist. In other words, he believed that Earth was in the center of the universe. Okay, he did not accept Copernican view, and in spite of the fact that he was the best astronomer in the late 16th century, it was in part due to the fact that he had built the best observatory in Europe and began collecting massive amounts of data, very, very precise measurements. Okay, and I'll show you what I mean in just a second here. And he collected all of this data, and what's so funny about the story about Tycho Brahe is that it is exactly Tycho Brahe's meticulous collection of data that enabled his student, Johannes Kepler, to be able to prove that Copernican view was accurate and that geocentric view was wrong. So despite the fact that Tycho Brahe had worked his entire life to try to disprove Copernican view, all right, and collect all of this data to support his theory that Earth was in the center of the universe, it was exactly his data that proved that Earth was not in the center of the universe, which is kind of an interesting argument. And I'll tell you a quick story about Tycho Brahe. This is a true story. I'm not making this up. So Tycho Brahe was this pretty well-known, pretty well-to-do, astronomer of his day. And he gets invited to the Danish king's court. He was Danish, okay? Tycho Brahe was Danish. He gets invited to the Danish king's court, and for Tycho Brahe, this is a big deal because, he's kind of, a middling class sort of a guy, so to be invited to the king's court, the Danish king, and meet the king of Denmark and be able to partake in the court festivities in the 1500s, this is a big, big, big deal for him, okay? And so he gets invited in the early 1600s, 1601, he gets invited to this court. And these kinds of festivals were very, very long affairs, okay? They went all day long. And there was all sorts of things, entertainment. They had court jesters. They had, multi-course meals where they bring out several different appetizers. They bring out wine. They bring out all sorts of different things. And Tycho Brahe, because of the system that he lived in during this, very, kind of, it's not quite full swing absolutism yet because we're still pretty early on in Tycho Brahe's lifetime. But in the 1500s, we haven't seen full absolutism take place yet. But he's living in kind of this quasi-absolutist time. There's these medieval traditions. It's a big deal to be invited to the king's court, and he does not want to be on anything but his best behavior. And as I said, these things go on for hours and hours and hours. And the true story about Tycho Brahe is that about, early afternoon, he had to go to the bathroom. But instead of excusing himself to go, to the bathroom, he did not want to be perceived as a rude guest. So he holds it. And he holds it, and he holds it, and he holds it, and he holds it all day long. Until later on that evening, around 9:30 or so, he finally is done with the court stuff. He goes and tries to go to the bathroom, and he can't, because what has happened is that his bladder ruptured from not going to the bathroom. And when his bladder ruptured, this created a massive, massive infection. And he died a couple of weeks later in basically delirium and with septicemia, because what happens is the infection gets into your bloodstream, and he died of septicemia as a result of his bladder exploding basically, or rupturing, and that's how Tycho Brahe meets his end. It's a rather sad end for him. And when Tycho Brahe dies, his student, Johannes Kepler, took up the reins and began continuing Tycho Brahe's work, except for developing new techniques to solve these math problems. So Tycho Brahe's quadrant, which you can see here how huge this thing is. Here's the size of probably a full-grown male at this time, which is, I'll say, somewhere in the area of about 5 feet 6 inches tall or so. And you can see how huge this thing is here. that allows him to get extremely accurate measurings on his quadrant of the movement of the stars, the planets, and so on. And so it's using this device here to be able to measure star movements over time that allows for Kepler to be able to come up with the solution to how all of these numbers fit together. And this allowed him to make minute measurements of the cosmos. And the King of Denmark actually gave Tycho Brahe the island of Hveen in Denmark to use for his observatory because it was remote and really ideal situation for observing the stars. And here's Johannes Kepler. He was the first great Protestant scientist. He was an assistant to Tycho Brahe, and he was the one to be able to mathematically prove that the heliocentric universe was in fact a sun-centered heliocentric universe. And he also, Johannes Kepler, came up with 3 laws of planetary motion. Don't get the laws of motion from Kepler confused with the laws of motion from Isaac Newton. Isaac Newton's laws of motion relate to basically all of physics, versus Johannes Kepler's are related to planetary motion. So what he comes up with are ideas like orbits being elliptical rather than circular in nature. This was one of the major mathematical breakthroughs that Kepler made. He said that planets do not move at uniform speeds in their orbits. In other words, as the Earth revolves around the sun, the Earth, as it gets closer to the sun, it speeds up, and as it moves farther away from the sun, it slows down. And the time it takes for a planet to orbit the sun is directly based on how far away it is from the sun. That is to say that a planet that is farther away from the sun is going to naturally have a longer period of orbit. It would not happen where a planet who is closer is moving around the sun at a more slow pace, and a planet that is farther away is moving at a faster pace. The planets move relative to how far away they are from the sun. And the farther away they are, the slower they move around the sun. All right, and here you can see Kepler's model of the solar system. And this is the frontispiece of his book, The Rudolphine Tables. And you can see that this image contains Brahe's island of Hveen on the base in the center, Gutenberg's printing press on the right, and the 2 newest columns dedicated to Copernicus and Brahe, and the older columns dedicated to such astronomers as Hipparchus, Ptolemy, and Aristarchus. Okay? Here is Galileo, and Galileo was the one to develop a new telescope using convex lenses to focus light over increasingly long distances. I just recently watched a really, really cool documentary, I believe on Netflix, but possibly on YouTube, of the history of the telescope. And the history, or maybe it was on Amazon Prime, I really don't know. But anyway, the point is that I watched this thing about the history of the telescope, and it was really, really interesting because I knew that I was going to be teaching about this. And basically, if you hold 2 magnifying glasses along in front of one another, like if you were to hold them out in front of you, the magnifying glass closer to you and the magnifying glass farther away, if you extend one arm out farther, as you look through both magnifying glasses, you'll see a center focal point of something far, far away. And it comes in very clear. And Galileo realized that if you used multiple convex lenses, all situated in perfect alignment with one another, that you could see really, really far away things like the moon much more clearly. And so, previous to this, people thought that the moon was a smooth orb. It wasn't until Galileo, with his telescope, was able to zoom in on the moon and see that it's a rocky surface with a bunch of craters on it from being struck by space rocks, basically, right? Meteors and other things like that. And so people used to think that the Earth was like this smooth orb, but Galileo realized the surface of the moon was really textured and and rocky, just like Earth's was. And so he also developed laws of motion. Laws of motion, according to Galileo, though, had to do with acceleration and inertia. Okay, for as long as I live, I will never hear the word inertia and not think about my childhood growing up on Bill Nye the Science Guy, where in the intro to Bill Nye the Science Guy, there was a line that said, "Inertia is a property of matter." Bill Nye the Science Guy. Bill. Okay. That was such a great show for kids, by the way. Wow. I loved Bill Nye the Science Guy. That was a great show. All right. Anyway, so Galileo Galilei came up with these ideas of acceleration and inertia. The idea that is basically this: an idea that is more massive, or an idea, not an idea, an object that is more massive, okay? An object that is more massive is going to take more energy to accelerate. Think about cars on the road. If you have a small little car with a big engine in it, it's going to accelerate fast. If you have a big car like a truck, like a semi-truck, that's much more massive. It takes much more energy to accelerate that object. Same with inertia. Once an object is in motion, that mass helps to keep it in motion. So in the same way that a train or a truck, a semi-truck, have a huge amount of mass, once they get going, also due to their mass, they're going to be more difficult to slow down, okay? Because it takes more energy to stop them as well. And so as you are, riding in a train, and that train is going down the tracks, trains can't stop very quickly because there's so much mass keeping the train moving forward that it takes a ton of energy and time to slow that train down safely. These are Galileo's ideas about laws of motion, all right? Galileo's findings, though, started to become very controversial in the Catholic Church, and there was an inquisition, very similar to the way that they held the Diet of Worms for Martin Luther the previous century. There was an inquisition of Pope Urban VIII that forced Galileo to retract his heliocentric views that he had espoused in some of these works that he was publishing. And he agrees to renounce it at first, but then later releases a book where he acknowledges the validity of Copernican view because the science pointed to it. It was right, and he knew it was right. And when he does this a second time, he was then sentenced to house arrest for the rest of his life, which was about 9 more years of his life. So about 10 years before he died, the Roman Catholic Church sentences Galileo to house arrest, where he's not allowed to leave his home, and he's also not allowed to publish any more works that advance the Copernican view of the universe, the heliocentric view. And he dies in house arrest, and that was in 1642 that he died. Okay, so Galileo Galilei dies in 1642. Get this, though, the Roman Catholic Church does recognize the error in its ways, which is why, remember, he died in 1642. In 1992, when I was in second grade, the Roman Catholic Church under Pope John Paul II formally issued an apology to Galileo 350 years after his death, saying, "Turns out you were right, Galileo. Sorry about that." And so the Catholic Church does eventually, and when I say eventually, I mean in my lifetime, apologize to Galileo for sentencing him to house arrest for advocating fact. The next major figure from the scientific revolution we're going to be looking at is Francis Bacon. Francis Bacon formalized something known as empiricism. Empiricism had already been used by Brahe and Galileo, but Francis Bacon refines empirical study by using something called the inductive method for scientific experimentation. And here comes one of my favorite quotes of all time. Okay, it's a quote from Francis Bacon. Renounce notions, and begin to form an acquaintance with things. Renounce notions and begin to form an acquaintance with things. I love this quote. I absolutely love it. Basically, what Francis Bacon is saying here is get rid of superstition. Get rid of, beliefs based on emotion. Get rid of hunches. Get rid of common sense. Renounce notions. And instead, begin to form an acquaintance with things. Get to know things as they are, not how you want them to be or how you personally think they are. Okay? Begin to form an acquaintance with things. Collect evidence. Okay? That's what he's saying here. Inductive method. To this day, in scientific studies, we still utilize some of the techniques that Francis Bacon pioneered in empiricism with data collection and data relationships and so on and so forth. All right? All of these things have become important too in the field of criminal justice, where if you're trying to become a criminologist or a forensic scientist, to go to the crime scene and collect the data, all right, and investigate the data. And if the data works together to come to a certain conclusion, all right, that is the way to determine how the crime took place. Likewise, though, with the scientific revolution, we saw a new introduction of deductive reasoning. And deductive reasoning was less Francis Bacon and more this other guy, Rene Descartes. And between deductive and inductive methods, using the two in conjunction with one another, we come up with what we now know today as the scientific method. All right? So Francis Bacon's side of it is the inductive method, the evidence collection side of things. If we think of it this way, okay, think about what you're doing when you deduce versus induce, okay? If you are trying to induce vomiting, okay, if you're trying to induce vomiting, you're starting with somebody who is not sick and you're trying to make them sick by inducing them to vomit, okay? If you're trying to induce something, you're starting with nothing and then you're collecting things to try to make something happen, okay? All right? When we think about inductive method, we're clearing the table, okay? And we're trying to collect every bit of evidence that we can place on that table. And once we collect all of the evidence and the data, and we can start to analyze that data. Deductive, what are you doing when you deduce something? If you deduct something, you're taking something away, right? So with inductive, you're trying to add something. With deductive, you're trying to rule it out. And that's between the two of them, collecting evidence and ruling out other, tangential, unrelated stuff, okay? You come up with pretty good scientific method. Now, here you can see the frontispiece to the Historical Royal Society of London. And Bacon is located on the right over there, okay? And heck, that looks an awful a lot like Rene Descartes on the left, all right? So Francis Bacon on the right, Rene Descartes on the left, all right? And this Royal Society of London was one of the ways that during the Age of Absolutism, various, state governments, the Kingdom of England, the Kingdom of France, and so on, began establishing scientific organizations for the advancement of scientific knowledge and statecraft. Okay, in other words, making a stronger state. Now, Rene Descartes was the other guy that I was talking about. He lived from 1596 to 1650, and he wrote a very famous piece called Discourse on Method, where he advocated, like I said, using that other method, the deductive method. And to give you a little background on what I mean here, I think perhaps, well, I can't play a YouTube video while I'm streaming a YouTube video. So unfortunately, that's not going to work because the sound won't come through. But let me explain to you what Rene Descartes did. We have to understand that Rene Descartes was a man of his time. And because he was a man of his time, he was hopelessly wrapped up, intertwined with all of the religious hysteria of his time during the early 1600s. Now, Rene Descartes was French, okay? And so, we know that in his lifetime, France had gone through, some pretty serious upheaval in the French religious wars, persecuting against the Huguenots and things like that. And because he lived in this highly religious, superstitious time, and because anatomy, the human anatomy, hadn't been 100% figured out in terms of how the body actually works, one of the things that Rene Descartes believed in was this notion of spirits. Okay, and he thought, Rene Descartes, after extensive analysis of human cadavers, corpses, okay, he came to the conclusion that the nervous system was infused with animal spirits, and that these animal spirits animated your nervous system to be able to be sensitive to things like hearing, touch, taste, sound, and sight. Hearing, smell, taste, sight, touch. Okay, there we go. All right. And that it was animal spirits. Then, the other thing that he believed in was this idea of, let's talk about this. So in the scientific revolution, there was a movement that started, okay? But I need to be clear about what this movement was. Maybe you've ever heard of the term skepticism. It's good to be skeptical of things, at least to a point, okay? It's good to be skeptical. If you're overly skeptical about things that don't require skepticism, that's when I would say skepticism has moved into the boundaries of becoming less useful. And there's a lot of things that I could point to with conspiracy theories about that and that sort of a thing. But, there's been some recent studies about conspiracy theorists and various traits of their personality that they have that seemingly lend themselves to pretty fantastical thinking. And so anyhow, but there was this theory that came out at the time known as skepticism. And to be honest with you, we usually look at skepticism as being a good thing in science, right? But the kind of skeptics that we were talking about in this kind of skepticism was a very radical form of skepticism. A very radical form of skepticism that began to call into question the validity of the church's teachings. Now, Rene Descartes, being a religious man and being a product of his generation, did not take kindly to skepticism, because seemingly what skeptics said, he really didn't like skepticism because of the extreme version that it took. Skeptics in Rene Descartes' time seemingly kind of had this belief that like nothing was real. All right, skeptics, he thought that it was just like the ace in the sleeve, the constant ace in the sleeve, where any skeptic could just immediately come out and say, well, that's just because you believe it exists and I don't believe it exists. So skepticism was something that Rene Descartes didn't like, because he looked at skepticism as being very narrow-minded, very, it's like the argument no one can beat, right? And so oddly, here's the thing that's so great about Rene Descartes. Rene Descartes decides to combat skepticism by being skeptical of skepticism, which is really kind of itself pretty intriguing. But nonetheless, he basically says, I am going to set out to determine that skepticism is a bunch of blarney. Okay, it's a bunch of hoo-ha. Makes no sense. Okay, and so he basically says, how can I do this? How could I take on the view of the skeptics? How could I take on the view of the skeptics and prove, using their own view, that they are in fact wrong? Remember that Rene Descartes is trying to disprove what these people believed, these skeptics of this generation believed, which is that essentially nothing is real. Okay? So here's what Rene Descartes does. He says, well, if I were a skeptic, I would believe that there is some evil trickster demon. Okay, that there's some invisible, immeasurable trickster demon who is getting me to believe that things are real when in fact they may not be real. So he basically does this. He gathers everything, okay, and he puts it onto the table. Unlike inductive reasoning, where we clear the table off, okay, and we start putting things on the table, Rene Descartes takes the exact opposite view. He says, let's put everything on the table and one by one, run it through this little hypothesis of this evil trickster demon who is just tricking me to think that everything is here when it actually doesn't exist. And he starts taking one by one every little piece of knowledge that he has off of his table of knowledge. So he has this table and he's got a bunch of stuff on it. Bunch of papers, bunch of objects, bunch of everything on this table. And one by one, he starts examining each of these objects and running it through his little method that he's come up with, which is, can I be absolutely 100% sure that what I am holding in my hand is actually real? And one by one, he starts removing things from this table. Basically, he gets all the way to the end and his table is empty. And Rene Descartes takes a look at the table and he says it to himself, I cannot believe it. What if the skeptics are right? What if I am just being tricked and all of this is just an imagination, right? And none of this stuff is real. And he was very, very disheartened, but he wasn't going to give up. So here's what he does. He says, I need to find some piece of evidence to demonstrate that something is real. And he's thinking, and he's thinking, and he's thinking. He's like, what can I put on this table of knowledge? What can I put on this table of knowledge to demonstratively prove to the skeptics that things do exist and that we can't just be skeptical of the existence of everything? And his answer is right in front of him. He realizes, as he's thinking, wait a second, how do I know I'm thinking? I know I'm thinking because I'm the one who's doing it, okay? And so he comes up with this idea, cogito ergo sum, I think, therefore I am. Meaning that the way that Rene Descartes goes about disproving these skeptics is by saying, I know that I'm real because I'm the one doing thinking. The only one who can do my thinking for me is me. Therefore, I know I exist. And we cannot just be skeptical of the existence of things in the material plane simply because something might be tricking us out there, when in fact we know by way of our own thinking that we do in fact exist. I think, therefore I am. Okay? He also, Rene Descartes, demonstrated the relationship between geometry and algebra, as well as came up with this idea known as Cartesian dualism, which of course is named after him, Descartes, Cartesian dualism, where he divided all existence into the spiritual and material plane, basically saying that there are two realms that exist: the spiritual realm, which is a logical realm, and a material realm, which was this empirically based realm of objects, evidence that can be collected, measured, and so on. All right? And between Bacon's inductive method and Descartes' deductive method, we now have what we consider to be the modern scientific method. And the last guy that we're going to be talking about today is Isaac Newton, who, of course, of all of these figures, was probably the most significant. In fact, Isaac Newton may have been one of the most important names in all of history. Now, to be honest with you, Isaac Newton was a very, very peculiar man. Immensely intelligent, all right? Immensely intelligent, very, very smart, but extremely socially awkward. Now, we don't know for a fact, because they didn't have these kinds of diagnoses or medical knowledge back in the day, but it is extremely likely that Isaac Newton was severely autistic. He was a very strange, peculiar man. He was extraordinarily brilliant. He was very, very, very intelligent. This is not when I say that he was autistic, that has nothing to do with intelligence. Autistic kids can be very, 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 very bright, okay? And in fact, sometimes, can be geniuses, okay? That's not every autistic kid, but certainly it could be, all right? Autism isn't really about intelligence. It's about, it's a linguistic, social disability. And so he was, as an example, he was celibate his entire life. He had some very unusual views of women, and so on and so forth. So he was different, is all I'm trying to say. He was different, and his intelligence, of course, ended up resulting in probably the most important book that we will talk about in this entire class, which is known as Principia for short, or Philosophiae Naturalis Principia Mathematica, which is basically Isaac Newton's explanation of physics, all right? And I'll tell you another quick story about Principia, which is, as I said, it lays out the laws of physics, that even if you take physics in a modern day school, the simplest and most matter-of-fact way that we can describe natural phenomena on Earth's surface and in the cosmos is by using Isaac Newton's laws of physics. And Isaac Newton's laws of physics took into consideration new ideas about gravity, new ideas about motion. An object at rest will continue to stay at rest until acted upon by an outside force. An object in motion will continue to stay in motion unless acted upon by an outside force. For every action, there is an equal and opposite reaction. Okay, all of these ideas surrounding force, gravity, motion, and how objects move and relate to one another, the idea of mass being related to gravitational pull, and all of these ideas come out of Isaac Newton's work, Principia. And we call this very fundamental form of physics Newtonian physics, referring to Isaac Newton. Newtonian physics, there's no simpler way of explaining phenomena on Earth than using Newtonian physics. Of course, now we know, though, that where questions start to be asked that Newtonian physics does not have an answer for, we then needed to find new solutions for that. So the next major physicist to turn over Isaac Newton's theories and come up with an entirely new explanation of the universe was Albert Einstein in the 1930s, who came up with the theory of relativity, and talking about the relationship between time and space and the speed of light and other things like that. All right, and so these ideas are what we would now use. That, along with Max Planck and his idea of quantum physics, allows us to answer questions in physics at levels that Newtonian physics was unable to explain. All right, but for 300 years, well, almost 300 years, 250 years, Isaac Newton's piece, Principia, was the most convincing and important piece of scientific literature, required mandatory reading in every university for centuries because of how significant of a piece it was. And the story I was going to tell you about that, which makes it even more unique, is that it's a book that almost did not get made. And the reason it almost didn't get made is because Isaac Newton, in his lifetime, the Royal Society of London, and Isaac Newton was himself English, all right, the Royal Society of London was essentially bankrupt by the time that Isaac Newton wanted to publish his piece in the late 1600s. All right, and so let's see here. Actually, 1687. Okay, 1687 is when this was made. 1686. Okay, July 5th, 1686. Although down here there's a 2. So, sorry, I'm just reading Roman numerals really quickly. 1687 is what this says here, but this says 1686 up here. I didn't see that. Okay, anyhow, so in the late 1600s, at the time that Isaac Newton is trying to get Principia published, the Royal Society is basically bankrupt by this point. And they don't have the money to publish Isaac Newton's work. And that's the reason they don't have money for it, is because the Royal Society had only recently, a few months earlier, agreed to publish a piece by a guy named Francis Willoughby. Francis Willoughby wrote a piece called a book known as The History of Fish. Now, The History of Fish is an amazing book, all right? It's an amazing book with all of these really precise anatomical drawings of fish and really thorough and beautiful. A great book to have on your coffee table, okay? But in terms of its relative usefulness in explaining physics, don't get me wrong, there's probably some people out there who think that fish are more important than physics. However, the most most of the scientific community, I would say that having the fundamental piece to define all of physics for the next 250 years was going to be more important than a book on the history of fish. But the history of fish, they had made all these copies of it that no one bought, and so the history of fish nearly caused the entire Royal Society to collapse. And Isaac Newton, get this, in order for his piece to be made, he was so adamant that his book needed to be published. They basically say, well, look, we'll publish your book, but we don't have any money, and we can only pay you in copies of History of Fish, because that's all we have. And so it's an amazing story. That people a lot of times don't know about. Let's take a look at this here. History of Fish, Willoughby. Maybe my internet's not working that well right now. I don't know what's going on with this thing. Let's try the other one. Here we go. De Historia Piscium, History of Fish. All right, and here you can see some of the kinds of drawing. Oh, I guess that's pretty tiny. Let's see if we can find another here. History of Fish. Francis Willoughby, published in the Royal Society 1866. It was unpopular and sold poorly, causing severe strain on the finances of the Society of London. This resulted in the Society being unable to meet its promise to finance the publication of the very wealthy Newton's Philosophiae Naturalis Principia Mathematica, better known as Principia, leaving this to Edmund Halley, who was then the clerk of the Society. After Halley had personally financed the publication of Principia, he was informed the Society could no longer afford him to provide him the annual salary of £50. Instead, the similarly wealthy Halley was paid with the leftover copies of History of Fish. So it wasn't Newton that was paid with him, it was Edmund Halley who was paid with copies of History of Fish. But I told you I wasn't lying about it. Anyhow. Okay, so the principle of universal gravitation is one of the things outlined in Principia. All right, every body in the universe, meaning every planet, every star, every meteor, everything in the universe attracts every other body in the universe in a precise mathematical relationship. And since these natural laws are unchangeable and predictable, God's active participation in the natural world is not needed to explain the forces of nature. And this is what was so controversial about Principia, because Principia basically said, look, we can essentially explain most things that happen in the universe according to known, predictable, and unchanging laws of the universe that kind of have the universe ticking away like a clock forever in a known, predictable way. And a lot of the ideas laid out in Principia became the basis for the religious branch of the philosophical movement known as the Enlightenment. And so we'll talk about what deism is later. Deism is about as religious as this intellectual movement of the Enlightenment became. And a lot of early founding fathers of the United States, guys like Thomas Jefferson, George Washington, Thomas Paine, Benjamin Franklin, a lot of those big guys, they weren't really Christian. They were deists because they were students of this philosophy of deism that was kind of the more quote-unquote religious branch of the Enlightenment that essentially states, deism basically states that, sure, there's probably a creator. If you want to call that creator God, fine. But after God created the universe, since then, the universe has kind of been ticking away according to its own rules, very much the same way that when a watchmaker finishes making a watch, the watch kind of just ticks away and does what it's supposed to do as it was created, and there's no more interference from the watchmaker. That was kind of the deist view of religion. They're not really Christian because Christians believe that God intervened in daily lives, answered prayers, caused plagues, caused massive fires, caused famines, caused natural disasters. And increasingly, thanks to the scientific revolution, we began to attribute less and less and less of these scientifically explainable phenomena to divinity or to mysticism or things of that nature. So if you want a very easy memory device to remember all of these guys that we've been talking about up to this point, this will be good for you. It's a memory device. This is called a mnemonic device. Cops bring kids great big donuts now. Cops bring kids great big donuts now. That stands for Copernicus, Brahe, Kepler, Galileo, Bacon, Descartes, and Newton. And if you can remember those major 7 names from the scientific, those are scientific revolution thinkers, guys. Remember scientific revolution, guys. Don't get those confused with the Enlightenment thinker, guys, because unfortunately with this unit, well, maybe it's fortunately because maybe this is easier for you, I don't know. But unfortunately with this unit, we're stuck having to memorize a lot of names and their associated accomplishments. And that's why for today's assignment, what you're going to be getting is actually a vocab assignment, which I haven't done many vocab assignment with you guys, if any at all, except for maybe a quiz here or there on Canvas. But I'm actually going to be giving you a vocab assignment today pertaining to some of these terms that we want to begin to crystallize in our brains and remember to be able to use in future exams and throughout the rest of the class. So we're going to be focusing mostly on this first part on the scientific revolution thinker, guys. There are a couple of last names here that you may want to know about, though, in terms of other areas of scientific research that begin to be examined during this time. For example, anatomy and physiology, looking at the human body. Scientists in the scientific revolution began challenging ancient Greco-Roman medical views, particularly the medical views espoused by the ancient Greco-Roman anatomist Galen. And one of the most famous pieces to come out during the scientific revolution that challenged the ancient thinker Galen's views on anatomy was by Anton Vesalius. Vesalius wrote a piece called The Structure of the Human Body, which of course you could assume deals with the science of the anatomy of the human body. And he renewed and began modernizing the study of the human anatomy. And this opened the doors for others to follow in Vesalius's footsteps, to begin examining the functions of the various parts of the body. And I don't just mean like your arms, your legs, your head, or whatever. I mean internal organs, internal circulatory systems, and things like that. And that's how we get to William Harvey, okay? William Harvey wrote On the Circulation of Blood, where he began to explain how your blood is pumped by your heart and circulated throughout your body, all right? And so people were beginning to take a look at people's lungs, people's heart, people's circulatory systems, how the veins and arteries carry blood to and away from the heart, and so on. You also have Anton van Leeuwenhoek. Leeuwenhoek was the father of what we call microscopy. Microscopy. I know that looks like microscopy, but it's microscopy. You have to emphasize the syllable has to be on the right emphasis, okay? That's a joke. The syllable has to be on the right emphasis, right? Okay, microscopy, all right? And he was the first to see and write about microorganisms in water and the circulation of blood corpuscles in the capillaries and things of this nature, where he was able to look under a microscope and see things much smaller than people had seen before. But you'll notice that microscopes don't get invented until the late 1600s, okay? So all of these ideas here that we've been talking about were done in the absence of a microscope all the way up until right about the same time that Isaac Newton was coming out with his book, We're Coming Out with Microscopes. So whereas Isaac Newton was more preoccupied with the stars and telescopes looking into far, far, far distances, Leeuwenhoek and others were trying to look more closely at what was happening right here on Earth at a much, 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 much smaller level, cellular level, right? And then these royal scientific societies, governments and monarchs encouraged scientific inquiry as a means to further the prestige of the state and remain at the cutting edge of technology, because as we know, science and the state have a vested interest in one another. Now, we might not believe that much in recent times because it seems that currently the government seems to have a real problem with science, which to me is a very concerning development, because we want the science to be embraced by the government for the betterment of not only our society, but for the strengthening of our nation. And scientists within these royal scientific communities that were sponsored by the government could communicate with each other internationally. Because if you got published in the Royal Society in London, there was a good chance that you had membership as a French person or whatever to be able to read those works and even contribute your own works if you like. The Royal Society in England was probably the most successful of these royal scientific societies, and it was founded in 1660. Other royal societies started to be created later in Naples, Italy, France, Prussia by Frederick I, and then Russia by Peter the Great. So each of these royal scientific societies get created for the advancement of science and also technology for the increase of state prestige. So consequences of the scientific revolution. Well, of course, the scientific revolution is part one of a two-part series. Think about, if you guys are Star Wars fans, if the scientific revolution in Star Wars terms was Star Wars Episode 4, A New Hope, released in 1977, the Enlightenment is Star Wars Episode 5, Empire Strikes Back, released just a few years later. And so they are a continuation of the same story, but slightly different from one another. Okay, just the same way that Star Wars Episode 4 and 5 are a continuation, but tell different stories. And so we are going to be talking about the Enlightenment beginning next class. But consequences of the scientific revolution, it led to the Enlightenment. There were improvements in exploration during this time, as well as navigational technologies continue to be improved. There's a brand new invention known as the chronometer, invented by John Harrison, which gave mariners now the ability to determine not only their latitude on Earth's surface using older objects like sextants and compasses and other things like that, but now by using the chronometer, they can also determine the longitude, how far east or west they were of the prime meridian running through London. And so this was Harrison's sea watch with a winding crank that allowed for mariners to be able to determine how far east or west they were of the lines of longitude. Also, new experimentation during the scientific revolution helped to accelerate the agricultural revolution. We do begin to see very, very, very small improvements in medical knowledges that later on in the 18th and 19th centuries began to open the door to even more medical advances. But I need to stress to you that when we think scientific revolution, I really don't want you to think too much about medicine, because they don't have, it's not like pharmaceuticals or anything like that yet, not for a very long time. We don't really see pharmaceuticals start to come about until the late 1800s. In this time, though, they are discovering new understandings about biology and new understandings about human anatomy and the functions of the organs and how they work and stuff like that. So those are technically medical knowledge, but I don't want you to think of it like hospital medicine type of knowledge. We still have to understand that people's treatments for illnesses and their understanding of what causes illnesses and how to fix them is very, very, very rudimentary at this time. Now, also, we have to admit that the scientific revolution contributed to the end of those witch hunts that we talked about. So the scientific revolution is certainly not going to be a cause of the witch hunt, well, not directly at least, but it definitely will contribute to the end of the witch hunts as people begin to understand that witches are not a real thing, because witches are, in order to believe in witches, you have to believe in nonsensical, mysteries, ghosts, and other spirits and magic and all of that other nonsense that doesn't exist. And so, yeah, this contributes to the end of witch hunts because people will realize, like, okay, they're not really witches. All right, and then the science, and we have to understand, too, that the scientific revolution brought about a conflict, okay, between science and religion. Now, they weren't in acute conflict with one another until really we get to the 1800s, 18th or 19th centuries. But increasingly, science is going to pose a threat to religion, because as science begins to explain more and more and more things, religion is able to explain less and less and less things. So that's kind of how we begin to see secularism emerge in Europe. Now, secularism had been previously a focus on non-religious things that we talked about before, art and things of this earth, creations of humans. But remember that they still remain very, very religious in the Renaissance. But as we move on, people are going to turn away from religion and become societally much more secular, much more earth-oriented, much more what's going on here and now in this life, rather than living their life to be completely preoccupied with the afterlife and their faith. So we see a move away from the religious fervor after the scientific revolution, and religious institutions, they take exception to that, right? Because they don't want to see their influence and control over massive populations of people dwindle, but it does, particularly in Europe. All right, guys, that is going to do it for my lecture today. I just want to say thanks so much for tuning in. I hope you all have a wonderful Monday. I'm feeling great today because we've got that extra hour of sleep over the weekend with daylight savings time, and so I was happy to be able to come in today and teach from my classroom, and I'm feeling nice and well rested heading into this week here. I hope you guys are too. I'll be putting up that vocab assignment for you on Canvas, so make sure that you're checking that out, and we'll talk to you again here soon. Thanks, everybody.